Great. So welcome everyone to today's NPI monthly Zoom. And we're going to have a talk today by Hyojoon Kim from Princeton. And Joon's in an interesting role at Princeton. After getting his PhD at Georgia Tech, he came to Princeton as a cyber infrastructure engineer in our Office of IT, and now is in a hybrid role where he's sort of a research scholar in computer science, but also continues to be affiliated with the Office of IT, which is allowing him to pursue some really interesting interdisciplinary research on campus network management. And you're going to hear a little bit about that in his talk today. Just before we get started, a couple of logistics for doing this on Zoom. If you have any questions, feel free to either use the raise hand button or to ask a question in the chat. And we can either pull up a set of questions and have us interrupt Joon at some point in the talk, or take questions in the middle that are clarification. So Joon, if you want to stop at some point during the talk to see if people have questions, that'd be great also. So I think with that, why don't we let you take it away?
Cool. I assume everyone can hear me right now. So
okay.
All right, let me share my screen. And hopefully that's visible. All right. Cool. So I'll get started. So hello, everyone. My name is Hyojoon Kim. And today I will present the work happening at Princeton University called the Princeton P4 campus. So what is P4 campus? In a nutshell, it is an initiative to create and deploy experimental, but still useful network applications on a production network, because we primarily use P4 and programmable data planes. And because the production network in hand is a campus, we call it P4 campus. Why did we start this initiative? It's because we identified a big gap between research and production network. And I'm sure everyone is quite aware of this. Let's say a researcher came up with a new idea. Usually it's tested with small and unrealistic experiments, but it can still be a good idea. But the shame is that it actually rarely get a chance to get deployed on the production network. Meanwhile, the operator is very busy maintaining and troubleshooting the real network using outdated tools and practices. So this is a known issue. There's another issue. The researcher might came up with a bad idea too, and even published papers on it, but it remains bad because it actually didn't have a chance to get tested on a real network with real traces. So what's really missing here is a positive feedback between research and production network, where if there is a good feedback, both can mutually benefit each other. To elaborate more on this, let's look at the network research pipeline our group tries to follow, and I'm sure a lot of researchers have a similar pipeline. First, you come up with a good design and idea, and then you try to test it with the software with simulations like emulators like NS2 or Mininet or P4-BMV2. The next step is to try to do some controlled lab experiments with synthetic traffic using a real hardware, hopefully. And then the next step will be to do some realistic lab experiments using real traces. And the last stage would be a real deployment with production live traffic. What's really important here is that each stage has a feedback loop going back to the idea and design, so that the researcher can refine his idea or her idea and make it better. So the first two stages are quite okay to get to, but the last three stages are hard to get to actually. And because of that, we rarely get a feedback loop from these last stages. And to quote Jen, it's hard to eat your dog food, so you keep drinking your own Kool-Aid, which is a shame, right? So, and I totally agree with this. We are in a better shape now, though, because our community were able to create this cool P4 ecosystem where researchers and operators and developers can use an open spec language called P4 and make cool ideas possible using programmable data planes. And what's also cool is that you have multiple targets now. The first one is, of course, the P4C reference compiler, where it makes P4 programs runs in network emulators like BMB2 and Mininet. But now we actually have real hardware. For example, Barefoot networks have a Tofino chip, which is in the edge core wedge 100BF, and there's more switches, I think. There's also a P4-2 NetFPGA compiler so that you can run P4 programs on a NetFPGA SUMI targets. There's SmartNICs from Metronome. Xilinx is another NetFPGA variation, I believe, so that it's capable of running P4 programs on it. Because of this cool ecosystem, we kind of cleared the third stage as well. Now it's possible to run some control lab experiments using real hardware, realize your idea, and run some synthetic traffic to test your design and program. But it's still kind of hard to get to the last two stages. And without these last two stages, new ideas barely see the light outside of the lab. So we still have this problem. It is not a surprise that it's hard to get real traces and real deployments going on. There's multiple reasons for this, but just to point out some three major ones. First of all, getting a real deployment in a production network is disruptive, right? In operational networks, it's all about uptime. You have to make sure it's running, and putting something experimental or testing on a production network it's bound to be a bit disruptive. Second point is about user privacy. There are some personally identifiable information in the production traffic, like, for example, IP addresses and MAC addresses. So operators will not and should not share raw data with researchers. There is also generally a lack of collaboration and communication between the IT departments and researchers, which also makes it harder to get real traces and real deployments going on. There is an alternative, and just a really great alternative too, is to have a dedicated testbed. And some great examples are Planet Lab, Genie, and more recently the Fabric testbed. What's really good about these are they are real networks and they are WAN scale. So if you want to run a test with WAN scale, these are really great. But more or less, they have some limitations, mostly because they have limited access to a production traffic as being an isolated testbed. So it's kind of hard to give up using a production network as a testbed. And in particular, we think a campus network as lab is a great idea because campus networks have some unique advantages. First of all, there's all sorts of traffic, right? There's science going on in the campus, so you have science traffic. Many places have data centers of their own, so you see data center traffic. You have students living in the dorms and staffs and living on the campus as well, so you do have residential traffic. And running a campus and a university or college is a business, so you also have business traffic. Campus networks are open and dynamic. It's open to public in general, of course, and you have many visitors and events happening throughout the year. These days, it's not that common, but normally there are a lot of visitors events, and because of that, there's a lot of BYOD devices popping here and there. And generally, it's an access network, so you actually see traffic closer to the user, not somewhere on the backbone link, which is also unique. There was some discussion about enterprise versus cloud. Some people say campus or enterprise networks are dead because all the services are moving to the cloud. I don't necessarily totally agree with that, although there's some truth in it. I think there's still value in enterprise networks as an access network, right? And also a lot of solutions that run on enterprise networks are still applicable to cloud networks. For example, let's say you want to measure latency, ongoing latency, or you want to detect a microburst. You still want to do that in the enterprise and cloud networks. And it may be actually a bigger win if you can do it in the cloud networks and when you're troubleshooting your service. Campus networks are research friendly, of course, because this is the screenshot of our IT department webpage. It actually starts with enabling research, right? So they actually want to help with enabling research, and they're open to new ideas mostly. And because of this, there are existing mechanisms on campus to enable research. For example, there's an IRB process in Princeton. There's also the Office of Institutional Research, which helps with the procedure of getting unrealistic data for your research. And I think there are some other universities which have similar procedures as well. So this talk is actually about jumping the research chasm between research and real campus deployment, jumping over the disruptive privacy and lack of collaboration limitations, so that we can finally get to these last two stages and get feedback so that our ideas get refined and get better. And also, of course, help the production network do better jobs. So we will, through this talk, we will share our experience while doing so, and I'll try to follow this outline where try to be less disruptive, preserving privacy, and how to instigate more collaboration with the IT department. And we also share some results of our successful deployments, our experiments. We have a multiple programs, P4 applications running on our campus. First two are OnTest and the Flow, StarFlow, which are actually more enablers because they enable live traffic anonymization and efficient data collection. We have a bunch of passive traffic analytics apps for heavy hitter microburst monitoring RTT with fingerprinting or counting traffic by domain name instead of IP addresses. We also have an active traffic experiment, which is more bold and courageous. It's an in-network traffic obfuscation. We have a bunch of stuff, but because of the time limitations, we will mostly focus on the P4-RTT one and the PINOT. We'll dig deeper into those ones in the latter part of the talk. Of course, so this is something important, that our source codes are open to public. Our P4 applications, libraries, and modules are open source, including the codes for Tofino. This is because of the awesome move on Intel and Barefoot Network that they allow you to actually publicly open source the codes for target. And for example, if you go to the P4 campus website and drill down to some application, you will see some links to some codes. You may see some missing ones, but mostly that's because we're cleaning up the code or cleaning up the documentation, or it's in work in progress. So, but whenever it's ready, we're going to post the link to the codes. Okay, so we'll start with this first point, how to be less disruptive and using passive monitoring as a gateway drug. Another quote from Jen, I like it. Passive traffic monitoring, so what does that mean? So Princeton Network is connected to the internet like this. We have two ISPs, two connections to Internet 2, and a connection to Energy and Science Network. In our network, there's two border routers, two firewalls, one core router, and two data center routers connected to each other like this. What's important here is that we have network caps, or called test access points, which are actually physical devices attached to these links. And what they do is they basically copy and mirror the traffic that is shown on that link, and which appears on that link. And it's all bidirectional capturing. And although there may be some difference in scale, this is not unique to Princeton, I want to point out. So how Princeton does it, basically, you have a bunch of taps going on and mirroring traffic to a packet broker system. And the IT department uses that packet broker system to apply some policies so that they can select some mirror traffic they want to look at and forward it to their traffic analysis tools. As I said, this is not really unique to Princeton because all operational and production networks have some monitoring going on, and looking at mirror traffic is important. So there may be some difference in scale, but I'm sure a lot of campus networks have a similar setup here. So what we did is basically we asked for a small sleeve of that packet broker system and asked, like, can we also get that mirror traffic and feed it to our testbed in our campus? And we said we can load some P4 monitoring apps on the Tofino and feed the mirror live traffic as input. so that we can actually run our programs against live production traffic. And we were actually able to convince the IT department to do this for us. And why did it work? I guess it's because, I'm pretty sure because it's kind of low risk in terms of technically to the IT department, because there's little or no disruptions, because it's just mere traffic and they already have the infrastructure. And compared to that low risk, there's high return. And we used a bunch of real-time traffic analyst apps as a gateway drug to the IT department because, and as you can see, a lot of our apps are actually started as only runs against passive mirrored traffic. And it's kind of worked because we were able to output some interesting real-time analytics, which we're not able to do in the IT department's tools. So we were able to give some good results using our research projects. So this kind of worked, and I just want to give some tips on mirrored traffic. TAP is always better than port mirroring, which is also called span. Because span is something you configure on a switch, and span burns a port and resources on the switch. And if the switch also gets busy, it may influence the span mirrored traffic. So TAP is much better when you try to do this. A packet broker system helps a lot. You can apply some interesting filtering policies so that you can select and choose what kind of TAP traffic you want to see. It helps remove and mask the payload, which you want to do generally. And also it removes duplicate packets if you're tapping from multiple points on the network. So I want to ask, like, if this is a good strategy to go, I want to ask our colleagues, if you want to look into this, you can actually try to talk with some IT department staff and see what kind of monitoring systems they have and see whether you can actually convince them to make this happen. And because I'm quite sure they have something there, and it's a low bar for them. Okay, so of course there's privacy, so I'll talk about that, presumed privacy. So it's the art of navigating campus traffic data access. So there's two things. There's institutional review board, which is more about rights and privacy and welfare of human subjects. On Princeton, there's also an institutional review panel for the use of administrative data in research, and we call it PATTER. This is more about feasibility, how you do it, value, risk, and compliance. But the PATTER actually requires you to clear the IRB first. So let me talk about IRB a bit more. So when you're preparing your IRB application, I think it's important that you show you cannot access the raw data. This is very important. You say you're going to anonymize every MAC address and your institute's IP addresses. You probably don't want to anonymize non-institute's IP addresses because sometimes the destination is important, right? But you have to make sure you will anonymize your institute's IP addresses. Payload will be removed. If not, you will ask the operator to run some scripts and programs for you and provide aggregated results. So having these kind of statements in your application is very important. And you also want to show that you'll take good care of the data, meaning that even if it's anonymized, it'll be stored and processed at the machine managed by the IT staff. If not by a staff, it's going to be well managed so that you don't. This is to actually prevent you from copying data here and there and losing track of it. So I think it's really good to practice to say that you're going to take good care of that data. The use of unrealistic data is something at Princeton. It's more about feasibility, how and where you're going to get the data. Is there any costs? What's the value, motivation, or broader impact? Is there any risks? Is there any sensitive prepared data that belongs to Princeton? Does it comply with the law, US law, and all that stuff? I don't want to dig in too much about this, but feel free to go to that link and try to read what Princeton has. I think I tried to do some searching. I think I found some schools which has similar processes, but it's really important that you also just add it to the IRB. It's also good to try to figure out what's the procedure in your institute and try to follow that. The applications is not that different, although it's separate from IRB. It's actually not that different. Okay. Before I go into some technical stuff here, maybe I should stop. This is a good time to stop. And if there's any questions, please let me know right now.
Any questions?
Yeah, I have a question. How is where and how is the payload removed? Is that done at the tap?
Oh, that is done by the packet broker system.
By the, I'm sorry, what did you say?
The packet broker system.
Okay.
Yeah, so so Princeton does have a packet broker system. I think there's multiple vendors out there. Princeton uses Big Switch. I think there's Riverbed, some other places too. These packet broker systems, what they do is like it allows you to use a web GUI so that you can create a policy, so that you can do some filtering on the tap traffic and apply some filtering rules. And also you can have a service, they call it services. You can have a service to say like, okay, feed that traffic to some service node so that it scrubs the payload before sending to the researcher. And things like that. So they have some good services out there.
Great, thank you.
I do have a question. I think for the tab that you're saying, you probably have to make sure that the capacity for your tab is higher. Sorry, the capacity of your switch is higher than the tab, right? Because if otherwise, then you overflow.
That's true. That's true. But mostly our switches to Tofino, so we have a bunch of edge core switches which have 100 gig ports on it, like 32 100 gig ports. So mostly it's fine to consume that. Of course, if you're talking about the journeying along to our switch, yes, we have to make sure that pipe of tunneling that mirror traffic to us, it has sufficient capacity. But most of our links on campus are 10 gig or 40 gig or 240 gigs. So mostly it's fine for us. But yes, you have to make sure you have enough bandwidth on forwarding that mirror traffic. Also, you have to make sure you have enough processing power at the service node when you're scribing payloads and all that stuff. Yes.
Thank you.
Cool. Any more questions? Then I'll just move on. Thank you for the questions. All right. Okay. So let's talk about data anonymization, which is very important too. So everyone might know KIDA. KIDA is a really good place where actually they also publish data, right? Public real trace data up there. And so they really have good practices, best practices, and offline tools listed in their website. I encourage you to go there so that you can learn their practices. And they also have a really good taxonomy of offline tools you can use when you're anonymizing your network traffic data. At Princeton, we use something called the OnTask P4 program, which helps us do live anonymization at the data plane itself. So what this program does is if you feed in a live traffic, it'll parse the headers and hash relevant fields, for example, the MAC address or IP address, so that the output is actually anonymized live traffic. And so that is safe to feed to the researcher. You can also configure through the control plane which fields to hash using a match action table. So for example, let's say you want to hash the source MAC address or destination MAC address. There's a separate table for that. So you can put in an entry saying, if the input port matches this, hash the source MAC address. If there's no entry, don't do anything. So that's how you can control the policy without reloading a program with a special policy in it. For IP addresses, we can also do a little bit more flexible things. You can say if it matches this prefix, please hash it. The hashing is also prefix preserving, meaning let's say you say /16, it will keep the upper 16 bits, but hash the lower 16 bits. You can also turn that off. So it's quite flexible on what you want to anonymize. And so this is mostly what we use at Princeton. Recently, we integrated this program with a thing called Starflow, which is a work from John Sonchak, who's a postdoc at Princeton right now. He has a great paper on using the XTC on this. What it does is like, okay, OnTask will anonymize the packet, but it's still a packet stream. So if you capture it as a PCAP file, even though the payload may be removed. What Starflow gives us, it'll spit out grouped packet vectors instead of a packet stream. So what that is the compact flow data, which uses less storage, but it also enables faster analysis. So let's say you can have a server or a disk space or even a data plane, which is consuming these group packet vectors anonymized. And you can also run some monitoring apps on it to do near real-time analysis. You can also make it collect a lot of data. So we've actually been collecting data since May 14th, which is more than 3 weeks now. And I think we have around 20 to 25 terabytes of data when tapping 1 to 2 gigabits per second link. So that's, if you think about you're going to capture a PCAP file for that, that's much more. But using this, we don't lose a lot of information and still use less storage. But if you're more interested, you can look at these papers and read it off. They have some good information with more detail as well. All right, so that's how we do that data automation at Princeton. Let's talk more about collaboration with YT. So this is what worked well at Princeton. So it's the strategy is to have a joint position between computer science and IT department, right? So a person with 2 hats. As a CS staff, the person can have access to research projects and come up with new ideas, but also as an IT staff, he or she can have access to the campus network and also convince the IT department to do some creative stuff for them. Also, of course, they have to make sure it's not that crazy. And this kind of worked well for us. That person is me at Princeton. And if there's something similar and other institutes, I think it will work well. It's worth looking into. And also what's important is to try to find problems that matter for the IT department. For example, at some point, our operator got tired of anonymizing traffic data for us, and it was harder for live traffic. And that's why we worked on this program called OnTask, so that we can do traffic anonymizations in live stream, and we can do it for them. Also, there was also a problem with occasional packet drops at Switch. IT department was having some trouble, but not sure why was the reason. We had a program called Conquest, which is for queue monitoring, a P4 program. So we were actually able to confirm this was because the queue in the Switch was being filled up because it was being overused by some application. A big thing in our Princeton network right now is doing Wi-Fi first. We try to do a Wi-Fi first, meaning that we're trying to move a lot of things on wireless and then only put something necessary on wired. So big questions are, where is the bottleneck in our Wi-Fi infrastructure? So we're having talks with the IT department to use another P4 program called P4-RTT to measure the round trip time latencies at different vantage points so that we can actually pinpoint some bottlenecks in the Wi-Fi infrastructure at Princeton, and so on and so forth. So I think it's really important that you try to also find problems that matter for the IT department, which instigates more communication collaboration. Cool, so using these strategies, we were able to kind of reach these last 2 stages and finally get that feedback loop. We were able to get some realistic experiments using real traces and also get some real deployment with live production traffic. I'm going to talk about some successful deployments we had on campus. Two of them one is passive monitoring called P4-RTT. Another one is a more bold one called active experiments called PINOT. So I'll talk about these two applications in this talk. And maybe before this, are there any questions?
I have a question.
Yeah.
So I'm wondering if you deploy this features into the campus network as a kind of real production kind of feature, so will you just also offer the kind of reliability or operation, or what happened when the feature has some problem and the user complains? So will you just mean that you will build up a kind of operation team and handle all this online kind of thing? So how it works in the campus network?
So so most of our applications were just passive. We started with passive monitoring apps, right? So even if something goes really wrong at our program, it didn't actually have any disruption to the production network, right? Because the things we touch are the programs that run on the Tofino hardware. And the campus networks is just forwarding traffic to us, mirror traffic to us. So even if there's something probably go wrong on our side, it didn't have any huge impact to them. I think some question may came up, like, what if your anonymization stuff is not working correctly, right? Let's say so what we do here is I'm the person with two hats, and because I'm also on the IT staff, I'm the one who would run these anonymization, right? So even if there's something goes wrong, I will be responsible. So I'm basically the firewall kind of thing, so that the researchers are kind of free from, and nothing really happens much. So for the anonymization, I would run on the switch only I can access when the raw traffic comes in, and then make sure everything is anonymized correctly, and then send it to the researcher. That's how we kind of do damage control. And most of the things we do did not have huge damages. I think we do carefully review our process and make sure nothing will happen before we actually jump in. For the active one, yeah, like we'll talk about it more, but it was more scary, I would say, but nothing really bad happened, so I'll talk about that.
Thanks.
Any more questions? All right, so we'll go on. Okay, so first of all, P4-RTT. So P4-RTT is a program to continuously monitor the round trip times beyond the TCP handshake. For example, let's say you see a TCP handshake mostly, right? So between the local customer and remote host. Most of the tools just focus on the handshake of the RTT and be done with it. But there is much more going on, right, during the session. And you can actually measure the continuous RTT by defining the timestamp between the sequence and ACK exchange between the local customer and remote host. So P4-RTT program started with this. Just to give a bit more motivation, we did some we did some analysis using a tool called TCP trace. So this is offline stuff, right? So just to see, is there a variation on campus traffic? So this is actually an analysis done against our campus traffic capture. And it was done with the local host, which is 10.9. And that's anonymized IP address, of course, talking to Netflix. And the left graph is the leg between the Netflix and the vantage point we have on the campus. So it's actually measuring the vantage point on Princeton to Netflix to the internet. The right one is the measurement from the vantage point in our campus to the internal host in our campus. So the left one will measure the internet leg, while the right one will measure the basically our wireless infrastructure latency, right? So so we did some analysis here, and you do see some variations. Not huge on the Netflix side actually, but we do see some like spikes happening on our internal network. And, you know, around 20,000 sample where you see some jump there. There's also something on jump in 60,000. So we saw, okay, this is worth looking into because, well, if it's flat, that's good. We can confirm that the Wi-Fi infrastructure is fine, and our connection to the internet is fine. But if we see some variation, that gives us some idea where we can fix it. So how does P4-RTT actually operate? So you have two legs here actually, right? As I said, we call it the external leg, where the vantage point is here. And then the external leg is the vantage point to the internet, and the internal leg is the vantage point to the internal host. And you send tag traffic to the P4 programmable data plane where the P4-RTT program is loaded. You can use the control plane to configure which IP prefix and port ranges are for the home network. The external network is this. In case you want to focus on a specific application on the internet. You can also specify which leg you want to look into, and the egress port means where you're going to send that stream of RTT samples. And the output of this program is actually a stream of RTT measurements going to a collection and analysis server. So that's how P4-RTT works in a nutshell. In detail, what's happening in the data plane, so I'll try to explain that. So we use the P4 registers as a hash table. So how it works is, let's say we are looking at an outgoing traffic with a sequence number 1001 with length 3. That means that the expected ACK is going to be 1004. When we see that, we actually insert that entry in the register, which is like a hash table. We hash the flow ID and expected ACK, and also then save the timestamp as a value to that hash table. And later, if we see the incoming packet which has the ACK number, we will try to match an entry, find an entry there. If we do find a match, we'll subtract the timestamp to get the RTT and then erase that entry. If not, that's a miss, right? So this is basically a join of outgoing and incoming packet streams happening in the data plane. Well, that basic idea works, but there are some problems here, right? You can have the memory limit, like the size of the register. You can also have cache collisions, which will make the measurements incorrect. There's also some TCP quirks that makes it complicated. You have delayed ACK and selective ACK happening. So there are some challenges here. To overcome the memory limit, one technique we used was, we also figured out, like looking at the real campus traffic, many TCP packets don't receive a corresponding ACK. This can be because there's a lot of SYN flooding or some scanning happening, or it could be just generally there's not much things corresponding ACK in TCP traffic. So if you have too many packets with which will not match a corresponding ACK, that's wasting a lot of space, right? So we have a technique to lazily expire entry with a threshold. And what that means is, let's say an outgoing packet comes in and another outgoing packet comes in, and it sees an entry, but there's a hash collision because it's filled up, or there's generally just a hash collision. We will look at the threshold, and if it's over the threshold, then we will kick out that entry and put the new entry in. And we call it lazily expire because there's no separate process going on looking at the timestamps and evicting them immediately after the threshold. Doesn't happen like that. It only happens when a new packet comes in and there's a hash collision. And this is more efficient, right? You don't have a separate process doing it. It only happens when it has to happen, when it needs to happen, basically. Setting the threshold is some way of an art. So you have to actually look at the traffic and see what's the best threshold for that particular flow or campus. For us, we used the 99th percentile of the RTT value in our campus trace, which was about 500 ms. So for our network, we use that as our threshold. All right, so, but you still have a problem. You still have one register there. So we actually overcome some other limits and also the hash collision limits by using a multi-stage hash table. So multi-stage registers. So instead of having one register, we will have multiple hash tables using a different hash function at each stage, so that even if there's a hash collision, we'll continue to try until it actually finds, it goes to the end of the multi-stage and finds something there. And this overcomes the memory limit per register, first of all, and it also overcomes the RTT sample loss due to a hash collision, because now you have multiple different hash functions and which will reduce the number of the chance of having a hash collision. In our experiments, I think about 4 to 5 stages, 3 to 4 stages actually gives us the best results. I think in our campus trace, we were able to account for about 97 to 98% of all the RTT samples when compared with the ground truth using a different tool. So these are some really fresh graphs coming out right now. Like even today, some graphs are coming out today. These are some examples of P4-RTT giving out some RTT samples. So you can do some per application RTT measurement, for example. You can say we look at YouTube and it looks quite good, right? You can look at Netflix and how the RTT looks at Netflix. People are using a lot of Zoom even right now. So you can think about measuring the continuous RTT of Zoom and compare them with different applications and see how we're doing. So that's a value of having continuous RTT measurements going on. I think this is really fresh. This came out like maybe, today. So this was a measurement we did, an output generated with P4-RTT. It was a wired host to going to YouTube. The session time was about 13 minutes. And the left one is the external leg. The right one is the internal leg. And so you can see there is some variations, and we still have to look into this more to interpret it and double check. But I thought it will be worth sharing these results with the community.
Joon, there's a question about what the x-axis is of these various graphs.
Oh, sorry. Yeah. So the x-axis actually is, I was looking into these too. These are actually not timestamps. These are like samples. So we have to actually kind of fix this to, I not fix it, but I think it'll be interesting to also see like how it looks like in a real-time series. Okay. But the x-axis here is just the enumeration of samples. I think Sada, who's a PhD of Jen, is the one who produced these. He can correct me if I'm wrong, but I believe the x-axis is just the enumeration of the RTT samples.
Yes, that's correct. Those are just samples.
Yeah. Cool. All right. Did I miss anything? Maybe I was missing something on the chats.
Are there any other questions since we're paused?
Oh, sure. Yeah. Yeah. Are there any more questions?
Yeah, I'm wondering how do you handle the TCP curves? you mentioned. So
Oh yeah, well, so I don't want to get in too much detail about this because we're going to have a presentation of this later in SIGCOMM workshop too. But just to give some idea, like for the delayed act, I think. So delayed act happens when the act is actually delayed because it wants to actually group the acts together and send it together, right? And because of this, the RTT samples will greatly increase because the act doesn't come immediately. Even though it came, it's like kind of like it stays there. So to cope with that, RTT focused on, but this delayed RTT never happens if the packet sizes are full sized, close to the MTU size. Because that means that it immediately have to send, right? Because it's full size. So P4-RTT kind of came overcome that with only focusing on RTT samples which are full sized, right? So
yeah. So in short, delayed act kind of causes two different kinds of issues. One is some packets don't get any act because they're covered later by cumulative act, and that can lead to unsampled packets that eventually are lazily garbage collected.
Yeah.
And just like SYN flooding, that's another reason a packet might not get an ACK. And if a delayed ACK actually happens, like Joon said, you're going to sub-MTU packets are at particular risk for this because the receiver is waiting, hoping it might get more data before it wastes the time to send an ACK. So we just never insert samples into the data structure if they're below the MTU size to avoid getting erroneously large RTTs that are actually the delayed ACK timer rather than something real.
Yeah. So we focus on actually only collecting the things we think are correct, basically. Right? These work well with the YouTube traffic or like video traffic because most of the sizes of those traffic are big. But I think there are some applications where you see more delayed act and we'll have less samples. But for them, we'll have less samples.
okay, thanks.
All right, so as I said, it's gonna appear in the SPIN workshop. Danny Chen, I'm sure we're going to give you a great talk on that in August at SIGCOMM, virtual SIGCOMM. Cool. Okay, so now we'll talk about PINOT. Actually, I didn't check the time. Is the time okay? I think the time is okay. Okay,
you got about 10 minutes. Yeah.
Okay, I have 10 minutes. Okay, let me go. PINOT is an active experiments program. So we identified two things here. The user privacy is at risk because, for example, if you say a DNS query using a public DNS server, the adversary can actually hear that you're asking for that domain, right? We also identified a unique opportunity where there's modern protocols are shifting to connectionless protocols, right? For example, QUIC, you can see QUIC, which is actually using UDP, which is normally a TCP connection, but it'll use UDP to do the job, right? And we also see a WireGuard VPN, which is actually a UDP VPN tunnel. So what this means is IP addresses can change seamlessly using these protocols. And we're seeing a lot of them these days. So PINOT is a programmable in-network obfuscation of traffic. So what means that we'll have a switch P4 data plane in our network. And when the query goes out, it'll actually use encryption using a key to change that source IP address to a different one and send it to the public DNS server. What's also interesting is like this host can ask the same question to the different domain using the same local IP address, but for that packet, it'll use a different IP address. And we can do this per packet, actually. And that's possible using the line rate data plane, program data plane. And if you do this, even the adversary actually listens to the traffic, it's hard to pinpoint who's actually sending this query. And you can have multiple keys and just rotate them to make it even harder to break. So this is much stronger than NAT. Some people might think this is just NAT, but this is much stronger than NAT because it has a very good inscription scheme, not just like deterministic mapping. And also it's per packet. It can happen per packet. So what PINOT provides is a standard anonymity. You cannot map packets to a user. There's also packet unlinkability, meaning you cannot link or group packets that come from the same source. You are not sure now. There's a low deployment barrier because it's a one-sided deployment. You don't need the other side or destination running PINOT. It's also a low performance overhead because everything runs on the Tofino itself. Return traffic to PINOT is fine, even if you have multiple, even in face of asymmetric path or routing path, because a control plane can make the switch determine which keys to use and just synchronize that so that even if the return traffic comes, it can correctly decrypt the encrypted source IP. Cool. So it's a bit detailed on how encryption works at the data plane. This is how it works. So for example, for IPv4 to IPv6 encryption, you'll have the original IP address. You'll add some random padding to make it longer. You have a key set version, and using those, you do encryption. We use the thing called two-round even unsure, which is an encryption scheme that uses 2 independent permutation boxes and 3 independent keys, and mostly just does permutations and XORs, which is possible to run in the data plane. And to break this, you actually need 7 trillion queries to break it if the random padding is 32 bits. And as I said earlier, it's much more secure than just doing NAT. And NAT for UDP, if you look at the ITF, the recommended mapping is you have to make it for 120 seconds, which is 2 minutes. TCP, they say the recommendation is at least 2 hours to have the same mapping. Whereas encryption and data plane with PINOT, it can be per packet, and there's no problem with that. So we were actually able to do this using an active traffic experiment using our real switch and router outside of the internet. So what we did, we connected the host to our PINOT programmable switch and then send a query to the Google DNS. And so we got a /64 subnet from the IT department to play with. So that's why we were able to do this translations. And IT department was fine with this because we were able to give them some gateway drop first. And then they also wanted to see how IPv6 works. So we were able to convince the IT department to make this happen. So we will send the PINOT will actually change the source IP address, and we were able to actually successfully communicate with the public DNS out there, get the response, and the host was actually able to get the response correctly. And we didn't do this once. We ran a lot of tests. We also did some tests with WireGuard and some NTP servers because NTP is another protocol which is has some user privacy issues. So this was a really awesome active traffic experiment we were able to do on our campus network. Cool. So to summarize, this talk was about jumping the research chasm again, how to do things less disruptive, how to preserve the user privacy, and how to instigate more collaboration with the IT department. We had some real deployment successes on OnTask, Starflow, which is about anonymized data collection. I presented P4-RTT, which is about continuous RTT monitoring. We have PINOT, which is a secure user anonymity system, and active experiments, and we have much more on our list as well. Some future plans is to actually have a connection between Princeton and Cornell using NicerNet P4 switch fiber pack. We are also hoping that we can connect to the Fabric testbed network at some point, and hopefully other institutes can also join with this testbed. So please join our effort so that we can actually jump through the research idea and go to the real campus deployment. We want more applications coming up. Please go to the website, and we want more from you as well. So we hope we can do this together and join forces. Thank you. I'll take more questions as well.
So one question that came in on the chat relates to the RTT example that you gave, which is if you do this on the switch, how do you avoid having queuing delay, or expand on that to differences in propagation delay between the packet and the ACK that might contribute to in the Tofino switch itself? So what keeps there from being sources of queuing delay in the Tofino switch?
So the sources, sorry, I was trying to look at the chat window again. Could you explain that?
Yeah, so is there queuing in the Tofino switch that might interfere with the computation of the RTT?
Oh, I see. That's a good question.
And I was thinking that there's not, because we're only taking packets in at input at up to line rate, and the packets aren't forwarded. So there's no mixing of the traffic on on a contended output port, because there's no forwarding happening.
There's no forwarding happening. Yes. So the forwarding is of course happening for spitting out the RTT samples, but it's actually not mirroring traffic outside. So there's no contentions on the output port, right? It's going to be less traffic than the input. So there's no contention. So there's no queue or buffering. I believe there will be very less buffering and queuing happening on the switch, because the traffic is this is actually just feeding on a mirror traffic and not actually forwarding that traffic.
Any other questions?
Yeah, I have a question. It looked like from your round trip traffic measurements that you have most packets are within a very small window of round trip time, and then you have a few outliers, very small percentage of them.
Yeah.
Is that's accurate? Do you have like a histogram of how that looks, how the round trip times look, rather than show it like this in these graphs? It'd be nice to have almost all packets are within this little window, and then we have these outliers out here.
Oh yeah.
I'm wondering what that graph looks like.
Yeah, like so you're thinking about the CDF graph kind of like.
Yeah.
That's our to-do list. Yes. So I said we're still. Now we're actually applying this tool to doing some more traffic analysis on real traffic. These graphs are quite fresh, and that's a really good point. Yes, we actually are looking to generate some CDF graphs so that, like say like 90% is this, 10% is this, and that's a good point. Yes, we are working on that.
Great.
I don't have it right now. Sorry about that.
Okay, no problem.
Any other questions? Great, Joon, thanks so much. Really appreciate it.
Thank
We'll
you
have
very much.
another seminar next month. So thanks everyone for coming.
Thank you, everyone.